In one of the most famous young star systems in the sky, astronomers have found something that managed to stay hidden in plain sight. Using the James Webb Space Telescope, they uncovered a giant world inside the dusty Beta Pictoris system, a place scientists have studied for decades. This was not a routine discovery. The planet was not spotted first as a clean bright dot in an image, which is how most directly imaged exoplanets enter the story. Instead, Webb found it by reading the chemistry of light. Buried inside a noisy field of dust and glare, the telescope detected the atmospheric fingerprint of a planet that had escaped conventional searches for years. The newly identified world is called Beta Pictoris d. It joins Beta Pictoris b and Beta Pictoris c, making this only the second known planetary system where astronomers have directly imaged at least 3 planets. That alone would be exciting. But the deeper reason this matters is that Beta Pictoris d may represent a new way of finding worlds in places where normal imaging struggles. Beta Pictoris is a young star about 63 light-years from Earth. At roughly 23 million years old, it is a cosmic infant compared with our 4.6 billion-year-old Sun. Because it is so young, the system still carries a bright disk of dust and debris left over from planet formation. That disk has made Beta Pictoris one of astronomy's great natural laboratories for watching how newborn planetary systems evolve. For years, scientists already knew this system was special. Beta Pictoris b was one of the earliest exoplanets ever directly imaged, and Beta Pictoris c later added another major clue to the architecture of the system. Yet the disk itself never looked simple. It showed warps, structures, and a sharply defined inner edge that hinted some hidden gravitational sculpture might still be missing from the picture. That missing influence may now have a name. Beta Pictoris d appears to fit the long-standing suspicion that another planet was shaping the dust from within. The team behind the new discovery was not even searching for a third planet. They were using Webb's near-infrared spectrograph, or NIR-SPEC, to study the atmosphere of Beta Pictoris b. That detail makes the story even better. Sometimes the universe reveals its biggest surprises while scientists are trying to answer a different question. Webb's NIR-SPEC instrument can do something unusually powerful. With its integral field unit, it gathers both an image and a spectrum for every tiny patch of the observed scene. A normal image tells you where light is. A spectrum tells you what that light is made of, how hot the source may be, and even whether the object is moving toward or away from us. Inside those data, the researchers noticed something unexpected. Where they expected a smoother pattern from starlight reflecting off dust, they instead found a repeated set of peaks and dips. Those features matched carbon monoxide absorption lines, spread across the spectrum like a barcode. And that barcode is exactly the sort of signal astronomers expect from the atmosphere of a giant planet. This is the key twist of the whole discovery. Beta Pictoris d did not first announce itself through shape, brightness, or easy visual separation from the disk. It announced itself through chemistry. Webb effectively listened to the planet's atmosphere before anyone could clearly point to it in a traditional image. That matters because dusty systems are incredibly difficult hunting grounds. The debris disk around Beta Pictoris scatters starlight like fog scattering headlights, filling the scene with confusing structures and false signals. In ordinary imaging, those bright blobs can be deceptive. They might be instrument artifacts, clumps of dust, or background objects rather than a true planet. But spectroscopy changes the game. Instead of asking only, "Is there a bright thing here?" astronomers can ask, "Does this light carry the molecular signature of a planet?" That second question is far more discriminating. Dust can glow and scatter, but it does not mimic a full atmospheric barcode in the same way a giant planet does. The team then went further. Because the spectrum also contains motion information, they measured the object's radial velocity and checked whether its behavior matched something orbiting Beta Pictoris rather than a background star or brown dwarf. The answer lined up beautifully. Its speed, position, and alignment with the disk all supported the conclusion that this was a real member of the system. Follow-up observations added even more confidence. Using Webb's mid-infrared instrument, or MIRI, astronomers detected water vapor and methane, strengthening the case that Beta Pictoris d is indeed a giant exoplanet with a rich atmosphere. So what kind of world is it? Current estimates suggest Beta Pictoris d is at least about 2 times the mass of Jupiter. That makes it the smallest of the 3 known giant planets in the system, though it is still enormous by any human standard. Models suggest it orbits around 30 astronomical units from its star, roughly comparable to the region where Neptune circles our Sun. Among the 3 known planets, Beta Pictoris d seems to occupy the widest orbit. Yet even there, it still lies inside the inner edge of the famous debris disk. That positioning is important. If a giant planet lives there, it could help explain why the disk has such a distinct inner boundary and why some of its structures appear so oddly organized. In other words, this is not just a new world added to a list. It may be the missing dynamical clue that helps explain the architecture of the entire system. Beta Pictoris has fascinated astronomers for so long because it feels like a younger mirror of processes our own solar system once experienced. We cannot go back in time to watch Jupiter, Saturn, Uranus, and Neptune forming. But in systems like this one, we can watch similar processes still unfolding. Dust, gravity, orbital migration, and atmospheric chemistry are all on display at once. That is why a discovery like this reaches beyond a single headline. Beta Pictoris d gives researchers another anchor point for testing models of how giant planets form, move, and sculpt the material around them. There is also a major technical lesson here. This appears to be the first directly imaged planet discovered primarily through moderate-resolution spectroscopy. That phrase may sound specialized, but its implications are broad. It means future exoplanet searches may no longer rely so heavily on seeing a clean isolated dot against a dark background. Instead, telescopes can search for atmospheric identity inside visually messy scenes. That is powerful because the most interesting systems are often the hardest ones to image cleanly. Think about the challenge this way. If conventional direct imaging is like trying to spot a firefly beside a lighthouse, spectroscopy is like identifying the firefly by the exact color code of its glow, even when the scene looks chaotic. For next-generation exoplanet science, that is a profound shift. It moves the search from pure separation toward interpretation. And Webb is unusually suited to that job. Its sensitivity in infrared wavelengths and the design of instruments like NIRSpec allow it to extract structure from light with remarkable precision. This discovery also shows the scientific value of studying known systems again and again. Beta Pictoris was not ignored, obscure, or newly found. It was famous, heavily observed, and already considered one of the best-studied young planetary systems in the sky. Even so, Webb still found a major secret inside it. That should make us humble about how much remains hidden elsewhere. If a third giant planet could remain veiled inside one of astronomy's showcase systems, then many more worlds may be waiting inside dusty disks around other nearby stars. There is something almost poetic about that. The planet was there the whole time, shaping its environment, influencing the dust, and leaving clues in the system's structure long before anyone could confirm its existence. The evidence was indirect at first, almost like footprints in snow. Only when Webb examined the light deeply enough did the world step fully into scientific view. Another reason the discovery resonates is that Beta Pictoris sits at the intersection of several big questions. How do planetary systems assemble themselves? How common are giant planets in wide orbits? And how often do we fail to see them simply because our methods are tuned to cleaner, easier environments? Beta Pictoris d suggests at least some of those missing planets are not absent at all. They are hidden inside complexity. That idea could reshape target selection for future observing campaigns. Systems once considered too dusty or too cluttered may become prime laboratories for spectroscopic planet hunting. There is also a storytelling advantage for the public. Exoplanet discoveries often arrive as abstract numbers, orbital distances, and mass estimates. This one has a more visual drama. A young star, a bright band of debris, 2 famous giant planets, and now a third world pulled out of the glare by reading its atmospheric signature. It feels less like checking a box and more like revealing an unseen actor in a cosmic play already in progress. The system becomes richer, more understandable, and somehow more alive. Scientists will now keep analyzing the Webb data to refine the planet's temperature, chemistry, and orbit. The more precisely they pin down those properties, the better they can reconstruct the system's history. Did Beta Pictoris deform where it is now? Did it migrate outward or inward through the disk? How strongly does it perturb the surrounding debris? And how do its atmospheric ingredients compare with those of Beta Pictoris b and c? Those comparisons may be especially valuable. Finding multiple giant planets in the same young system gives astronomers a rare chance to compare siblings that formed from the same broader environment but ended up in different orbital neighborhoods. That can reveal how local conditions change a planet's chemistry and evolution. It can also show whether giant planets in a common system follow a simple pattern or a much messier family history. This is exactly the kind of layered science Webb was built to unlock. Not just isolated wonders, but connected stories that join formation, atmosphere, motion, and cosmic context. And in that sense, Beta Pictoris d is more than a newly discovered planet. It is proof that the universe still has ways to surprise us, even in places we thought we already knew well. For decades, Beta Pictoris has been one of astronomy's iconic young systems. Now it has become something more. It is a demonstration that planets can be found not only by where they shine, but by what their light says. In the years ahead, that lesson may help uncover many more hidden worlds. So the next time we hear that Webb has revisited a familiar star, it may be worth paying close attention. Familiar does not mean finished. Sometimes the biggest discovery in a famous system is the one that has been hiding there all along.